What if I told you there's a material that's so full of holes it's pretty much just empty space, but it's also strong enough to help solve some of the world's biggest problems? Well, that's the wild idea that won the 2025 Nobel Prize in Chemistry. We're going to dive into metal organic frameworks, or MOFs, these incredible invisible architects that are literally building our future, one atom at a time.
So why are these MOFs such a huge deal? Well, to really get it, you've got to understand what chemistry looked like before they came along. The Nobel laureate, Roald Hoffmann, he put it bluntly. He called it a synthetic wasteland. You see, chemists were masters at making single molecules, right? But trying to get them to assemble into these big, orderly, three-dimensional structures, forget about it. It was like trying to build a city out of smoke. Let me try to put it this way for you. Making one molecule, that's like having one perfect little Lego brick. And making a polymer, well, that's like snapping those bricks together into a long, straight line. But building a complex 3D castle with all these perfectly designed rooms and windows and everything, for decades that was just pure guesswork. It was a massive headache and one of the biggest unsolved puzzles in chemistry.
So how in the world did we go from this chemical wasteland to a Nobel Prize-winning breakthrough? Well, the journey actually starts with a clue that's over a century old.
You know, the seed for this idea was actually planted way back in 1913. Alfred Werner won a Nobel Prize for discovering that metal ions could act like these really reliable, predictable joints. Now, that was a crucial piece of the puzzle for sure, but the big question was still just hanging there. How do you use these joints to build huge, stable structures that were also, and this is the absolute key, porous, full of empty, usable space?
The answer would come from three pioneers who just refused to accept that wasteland as the final word. We're talking about Richard Robson, Susumu Kitagawa, and Omar Yaghi. Together, these guys were about to turn this massive chemical challenge into a whole new field of science.
Okay, so the first really big aha moment came from Richard Robson in 1990. What you're looking at here is his brilliant idea in action. He figured out how to pick the perfect metal joint and the perfect organic strut, creating these building blocks that would just spontaneously self-assemble into this gorgeous diamond-like network. And just look at all that open space. This was the proof of concept that just blew the doors wide open.
So this new class of material, it needed a name. They called it the Metal Organic Framework, or MOF for short. And honestly, the concept behind it is just beautiful in its simplicity. Just think of them as the ultimate set of molecular Legos. You've got your metal clusters, which are like the connecting hubs, and then you've got these organic molecules that act as the struts holding everything together.
So with this revolutionary new Lego set in their hands, chemists were no longer just lost in the wilderness. They were architects. They were ready to design and build structures with a kind of control they'd only ever dreamed of. And one scientist, in particular, was about to create the absolute icon for this new era.
And that brings us to Omar Yaghi, who created what is, without a doubt, the most famous MOF ever, MOF 5. I mean, look at it. By combining these simple zinc oxide hubs with organic struts, he built this perfectly ordered cube. It was incredibly strong, it was stable even at really high temperatures, and most importantly, it was just unbelievably porous.
Just how porous are we talking? Well, get ready for this. The internal surface area measured a staggering 2,900 square meters per gram. Now, to give you some context, that just absolutely dwarfed other porous materials they were using at the time, stuff like zeolites, which you might find in, say, a water filter. This was on a whole other level.
To really wrap your head around that number, imagine taking a single gram of this white powder, which is about the weight of a paperclip, and unfolding all of its internal surfaces. You'd be able to cover an entire football field. That's a completely mind-bending level of porosity. But here's the thing, Yaghi's real genius wasn't just in making one incredible material. It was that he created the instruction manual for everyone else. He called it reticular chemistry, and it totally changed the game. It took crystal making from this unpredictable art form into a precise, predictable science. Step 1, choose your hub. Step 2, choose your strut. Step 3, assemble. You could build exactly what you designed every single time. It was a revolution. And this slide right here perfectly shows you the power of that design principle. This is the isoretical series. So by keeping the metal hub the same and just swapping in longer and longer organic struts, Yaghi's team could systematically make the pores bigger and bigger and bigger, all while keeping the fundamental blueprint exactly the same. It was elegant, it was powerful, it worked.
But the story doesn't stop with just rigid cages. Our third laureate, Susumu Kitagawa, he introduced this fascinating new twist to the story, soft porous crystals.
He designed MOFs that were actually flexible. They could change their shape, kind of like breathing in and out, to capture or release specific molecules. So all of a sudden, these weren't just static containers anymore. They were becoming smart, responsive materials.
So now we have these incredible designable crystal sponges, right? They're ultra-porous, they're super stable, and some are even flexible. So the big question is, what can you actually do with a toolkit this powerful? What real-world problems can we solve?
Well, the answer, it turns out, is pretty much anything you can think of. MOFs are now being custom-built to tackle our planet's biggest challenges. You've got some, like CALF-20, that can literally pull CO2 right out of factory smokestacks. You've got others, like MOF-303, that can harvest drinkable water straight from dry desert air. Seriously, they're being designed to clean up toxic forever chemicals from our water, to safely store clean hydrogen fuel, and even to deliver targeted medicines right where they need to go inside the human body. The potential here is just massive.
So from energy and the environment all the way to medicine, MOFs are providing a literal framework for us to build a better world.
I mean, just think about that journey for a second. In just a few decades, chemistry went from being a synthetic wasteland to being more like a precision workshop. Thanks to the incredible vision of Robson, Yaghi, and Kitagawa, we now have this atomic-level toolkit that lets us build custom materials designed to solve our most specific, most urgent problems.
Their pioneering work really revealed a fundamental truth. The future of materials science isn't just about making things stronger or smarter. In so many ways, the future is porous.
So, the power is now in our hands. We have the molecular Legos. We've got the instruction manual to build almost anything we can imagine. The only real question left is, which of our great global challenges should we solve first?